So we've been talking about the electrophilic aromatic substitution reaction, and we've come up with a list of functional groups that we can attach to the benzene ring, and we've categorized them by their deactivating or activating ability. It turns out that there's a much broader range of functional groups that you can have on benzene rings, and I just want to organize them in order of increasing activation. So the most deactivating is the trialkyl ammonium substituent. Okay, then comes the nitro group, and that's about the same as the trifluoromethyl group. Right, then comes the sulfonic acid, followed by the nitrile, and that's followed by the carbonyl. That's followed by things like bromo and chloro. And then we have the acetate or carbonyl group in which an oxygen is directly attached. All right, then we have, if we continue this along in the next line, fluoro. Then we have hydrogen. And then we have other groups like this amide. We have the OH, which is about the same thing as the OR, so an ether versus an alcohol. We have the dimethylamino group, and then we have like an oxygen with a negative charge and a nitrogen with a negative charge. Okay, so we can organize these in terms of their activation or deactivation. So here's our center, here's our benzene, right? And we said that anything to the left of benzene is more deactivating, right? So these are all of the deactivators. And likewise, oops, I forgot one. Let's just move it in here. We have an R group here. These are the R groups. These are all activators. Okay? And so why is something deactivating and why is something activating? Okay, so deactivation occurs when you have induction through the sigma network. Right, so the examples of this would be bromine and chlorine and fluorine and trifluoromethyl. Resonance delocalization is also responsible for deactivation. Because it pulls electron density out of that pi system, right, out of the aromatic ring. And so these are things like the nitro group, the carbonyl, and the cyanide. So how about activation? Activation occurs when you have a lone pair, or let's say even a pi bond, that's directly aligned with the pi system, right, and can participate in resonance. The other case is when you have a sigma bond directly aligned with the pi system, and can participate in sigma donation. Okay, so we have the activators and the deactivators. And really, none of this tells us anything about where an electrophile will substitute if these groups were already on the ring. So let's say we were to take benzene, we were to put one of these functional groups on the ring. What would happen if we were to take those resulting molecules and then react them again with an electrophilic aromatic substitution reaction? Where would the substituent go? Right, so we want to understand what the regioselectivity of these reactions are. Okay, and this really has to do with something known as the ortho, meta, para selectivity. Okay, so this is the regioselectivity of the reaction. All right, so let's say we have some functional group that's already on the ring. Let's actually label it with a Y. And let's say we want to react it with some E+, some electrophilic aromatic substitution reaction. We could get three different products. We could get the product in which we're going to substitute that electrophile at what we call the ortho position. We could get that electrophile substituting at what we call the meta position. Or we could get that electrophile substituting at the para position. Okay, so the ortho is a 1-2 relationship, the meta is a 1-3 relationship, and the para is a 1-4 relationship. Okay, so let's take the nitration of phenol as the first example. All right, so let's say we're going to take alcohol that's already on the benzene ring, and we're going to do a nitration reaction. So we've got nitric acid and sulfuric acid. We've got two products that form here. One product is going to be the ortho nitrophenol, and the other product is going to be the para nitrophenol. And those are going to be in a 40 to 60 ratio. All right, so let's actually try to think about how this would occur. And in order to justify the regioselectivity, I'm going to say here you must draw all the resonance forms. Okay? All right, so let's do the orthonitration first. Okay, let's try to substitute the nitro group at the ortho position. Okay, so orthonitration. All right, so we're going to start with phenol here, and we're going to react it with our nitronium ion, nitric acid and sulfuric acid. So why don't we just draw out the nitric acid and we'll review how this is going to happen. All right, so we've got nitric acid is going to become protonated, right, by the sulfuric acid, right, and so that's going to generate, we still have phenol, that's going to generate a protonated nitric acid, like this. And then we said that the water is a good leaving group, and so we can generate then the nitronium ion. Okay, and this nitronium ion has a positive charge at that position. All right, so what's going to happen here is we're going to now try to substitute that nitro group onto the ortho position. Right, so orthonitration involves attack of the benzene ring, one of those pi bonds, attack that nitrogen atom, electrons are going to move up onto oxygen as a lone pair. Okay, so if we were to attack ortho, the sigma complex that would result would look something like this. Okay? So we attacked ortho, we get this sigma complex, or this rhenium ion, depending on how you want to call it, and we can perform resonance delocalization here. So let's do that. Resonance delocalization can occur to give us, let's say, movement of those electrons there. And I'm just going to label this NO2. We can get the electrons to move again. And then we can also get the electrons to move in this direction, in which the oxygen low pairs are going to move down in order to create a system in which you've got a doubly bonded oxygen. Right, so that's going to be a positive charge on oxygen. Okay, and so in total we've got 4 resonance forms here. And having more resonance forms, of course, makes this a lot more stable. And then, of course, you can form product by doing a deprotonation. And so let's just finish this out. We get loss of a proton here. How could we lose a proton? We could simply lose that proton there, and the driving force, of course, is the formation of the aromatic ring again. All right, so that's orthonitration. It looks pretty good. So let's now compare this to the other 2 cases, the meta and the para. All right, let's try metanitration. The orthonitration, there's a little bit of steric interaction here between the hydroxy group and the nitro group. And so because of that steric clash, or in particular the steric clash that occurs here between the attacking pi bond and the nitronium ion, we've got a slightly higher energy. This is fast here in the case of orthonitration. All right, so B would be metanitration. Okay, so we're going to start with phenol again, and I'm going to skip ahead to that part where I just have the nitronium ion. Right, but remember, you have to know how to make that nitronium ion from nitric acid and sulfuric acid. So let's say it attacks meta now. Okay, so in order to attack meta, I would take this pi bond, attack the nitronium ion. All right, so I've got now nitro, hydrogen, and I've got a positive charge at that position. Okay, so I've got 1 resonance form. Let's continue along. Let's move the resonance forms, move that positive charge around the ring. We get that resonance form, and then we get this resonance form. Okay, and then of course loss of a proton. To reestablish aromaticity, proton falls off to give you your product, in which you've got now metanitrophenol. Now the key difference here is that there's only 3 resonance forms. Right, so there are fewer resonance forms here, and so what happens is that this reaction doesn't happen. All right, so you don't get loss of a proton here. You don't even get the attack of the benzene ring to the nitronium ion. All right, so let's actually see if we can justify the paranitro. All right, so here's C, paranitration. So paranitration, of course, would start with the same set of reagents. So again, I'm skipping ahead into until the nitronium ion forms. Now I'm going to take that pi bond and attack. And what do I get? I get an uranium ion. Right there, and then I can move the electrons around the ring. And so there's 3 resonance forms there. But what I can also do is I can have an additional resonance form by taking the lone pairs on oxygen and stabilizing the positive charge that's at that ipso carbon. And so that particular resonance form is not viable in the metanitration case. Okay, so again, I've got 4 resonance forms. That's pretty good. It's about, it's exactly equal to the number of resonance forms that I had for the orthonitration. And then I can get loss of a proton, of course, to reestablish aromaticity, and I get my the para-nitrophenol product. Okay. And we said that these were in a 40-to-60 ratio. Let's take a step back, and so you're going to form a little bit more of the nitro product, which doesn't have that steric occlusion. Okay, so if we observed only the ortho and para-nitrophenol products, can we, devise a logical mechanistic reason for this regiochemistry? Well, we just did, right? Since the uranium ion is more stabilized when the nitro group adds to the ortho and para positions, because we have 4 resonance forms, these 2 uranium ions will form faster, right? So this is really slow here, but this is fast in the case of paranitration, right? So the activation energy needed to break the aromaticity is a lot smaller. There's another way of actually looking at this, and that's by looking at the electron density that's on a benzene ring. And so if we were to have a phenol, and we were to look at the proton and C13 NMR chemical shifts, right, we'll be able to determine which one of these groups, ortho, meta, and para, which one of those carbon atoms is actually more electron rich. Okay, so for the ortho position, the proton chemical shift is 6.78 parts per million, and the C13 chemical shift is 113.8 parts per million. For the meta position, all right, the proton is at 7.17 parts per million. Right, the C13 is at 129.4 parts per million. And for the para, the proton chemical shift is 6.82 parts per million, and the C13 is at 120.4 parts per million. All right, so you can clearly see here that the meta positions are more downfield. And we said that when things are more downfield, they have less electron density on them. So if they have less electron density on them in the first place, we can say that the ortho and para positions are more delta minus, and they're going to have a little bit more of an electrostatic interaction with that nitronium ion, which is positively charged in the transition state. Another way of looking at this is just by drawing the resonance forms for phenol. Right, so we can take the oxygen lone pairs, and what you'll find is as they resonate throughout the benzene ring, you're going to place negative charge on only the ortho and para positions. You never place that negative charge on the meta position. And so what you can say is that the ortho and para positions are indeed more delta minus. Right? And so those three positions all have greater electron density. And since rate is controlled by these electrostatic interactions, the ortho and para substitution occurs exclusively. Okay, so oxygen, that this phenol that we had on the benzene ring, this was an example of an activator already attached to the benzene ring. Right, it has a lone pair aligned with the pi system of the benzene ring. What would happen if we had a deactivator as a substituent on the ring? Well, the first thing that occurs is that the reaction is much slower because of the deactivating group. Right, this is going to lower that HOMO. But second, the deactivator would give us a set of resonance forms that favor the formation of the meta-substituted product. So let's actually draw what that might look like. All right, so we're going to start, let's say, with CF3, or a trifluoromethyltoluene. And let's say we do a nitration reaction, although it could be any one of those electrophiles. We're going to get exclusively in this reaction the meta-nitro product. We don't get any of the ortho or para. All right, so let's draw out the resonance forms. These resonance forms will tell us why this is the case. Okay, so let's do the first example, the orthonitration. Okay, so in the case of orthonitration, right, I'm going to again skip ahead to the nitronium ion is already formed. All right, if I do orthonitration, I'm going to attack that set of electrons. I'm going to get an arenium complex that looks like this. Okay, and then I can resonance delocalize around the ring. Do it one more time. And I'm left with 3 resonance forms. And actually, one of them is really bad, right? This resonance form here is really bad because the electrons are being pulled towards that CF3 group via induction. And so we don't want to make that carbon have even more positive charge. And so this is a destabilizing effect on the rhenium ion. Now let's see what would happen if we did a metanitration. Okay, so again, let's skip forward all the way to the nitronium ion is already formed. All right, again, I'm going to attack that carbon now. Okay, I'm going to draw my resonance forms. And so I've got nitro attacking at the meta position. I can delocalize around the ring. And go one more time. And what we'll notice here is that we have, again, 3 resonance forms. And so if we were to analyze these resonance forms with respect to the other 3, in the case of orthonitration, what we'll see is we don't really have any really bad resonance forms, right? Because the positive charge alternates on the different carbons. And so what can happen here is we can, of course, get loss of a proton. Right? So if we get loss of a proton, reestablish aromaticity, we're going to get the metanitro trifluorotoluene. Okay, so this reaction is fast, whereas this reaction is slow. Okay, and so slow that it actually doesn't occur. Okay, so we don't get any loss of proton to give us the orthonitro trifluorotoluene. Right, that does not occur. Let's see if this is the same case for the paranitration. Okay, so paranitration is this one. Skip ahead again to formation of that nitronium ion. We're going to attack with the paracarbon. We're going to get a set of resonance forms. Okay, so we have that resonance form to start. We can resonance delocalize. And we can resonance delocalize one more time. Okay, and then if we could get this reaction to lose a proton, we would generate the para nitro trifluorotoluene. But if we were to analyze these resonance forms, we would see that there are 3, right? So the same number, but we have one resonance form that is particularly bad, and that's this one. This one is really bad, and because again, you've got that trifluoromethyl group that is pulling electron density away from that positive charge, which is not going to stabilize that positive charge. Okay, and so this reaction is really slow, so much so that it actually doesn't occur. Okay, what would this look like in terms of a reaction coordinate diagram? Reaction coordinate diagram would look like this. So we've got trifluorotoluene here, and we've got formation of, let's say, the metanitro uranium ion, maybe like that. But the formation of, let's say, the ortho and para are going to be much higher. Okay, so they don't form because this activation energy is a lot higher, right? So we've got transition state here and a transition state here, and of course, if we're controlled kinetically, then we're going to go over the hill that is a lot lower, right? So the pathway leading to the meta product has a transition state that is lower in energy, right? Why? Because the trifluoromethyl group is strongly electron withdrawing due to its inductive effect. And so the rhenium ion will sense this effect more strongly if the positive charge is on the carbon directly attached to it, right? So we've got these carbons here, and eventually you can get a resonance form there that's pulling that electron density. So what does this all mean for regioselectivity in electrophilic aromatic substitution reactions? Could we categorize that long list of substituents not into deactivator or activator roles, but instead into ortho-para-directors and meta-directors? Well, here are a couple of rules that will help guide us. So what are the rules for regioselectivity? First rule is that all activators are ortho-para-directors. Right? So if you have an activator on the benzene ring and you do an electrophilic aromatic substitution reaction, the new electrophile will go to the ortho and para positions. Second rule is that all substituents with lone pairs adjacent to the ring are ortho-para directors. So this is irrespective of whether or not you're an activator or deactivator. If you have lone pairs that can participate in resonance into the benzene ring, you're going to direct the approach of the new electrophile to the ortho and para positions. The third thing is that deactivators without lone pairs adjacent to the ring are meta-directors. Okay, so let's draw out our reactivity series again, and let's try to assign whether or not these are meta-directors or ortho-para-directors. Right, so let's draw this out. So we've got trialkyl ammonium, we've got nitro, we've got about the same deactivation is CF3, then we've got sulfonic acid, then we've got cyanide, then we've got the carbonyl, then we've got bromo, then we've got chloro, then we've got the ester, right? Then we've got fluoro, then we've got hydrogen, there's our benzene. Then we've got the R group, alkyl group, then we've got the amide, then we've got the alcohol, which is about the same as the ether, OR. We've got then the dialkyl amino, then we've got the oxygen with a negative charge, and the nitrogen with a negative charge. All right, so here's our benzene ring. This is the center, and we said that all of these again are deactivators, and all of these are activators. Right. So to the left of benzene are the deactivators. To the right of benzene are the activators. Now let's try to assign the ortho-meta-para directing ability. So the first rule is that all activators are ortho-para directors. So we can just put in ortho-para in each of these places. That's pretty simple. Now, how about the second rule? So all substituents with lone pairs adjacent to the ring are ortho-para-directors. Right? So I'm forgetting my positive charge on that trialkylammonium. If we were to scan all of the deactivators, there are only a couple that have lone pairs adjacent to the ring, and those would be the bromo substituent, the chloro substituent, the ester substituent, and the fluoro substituent. So these four are going to be your ortho-para-directors despite being deactivators. And then the third rule states that deactivators without lone pairs adjacent to the ring are meta-directors, and so these are all going to be meta. Okay, so these are the rules for regioselectivity in the electrophilic aromatic substitution reaction. If you have one of these groups on a benzene ring and you do an electrophilic aromatic substitution with one of those electrophiles, those electrophiles will go to the positions ortho, para, and meta that are directed by the groups that are already on the ring.